Welcome, everyone. Today, we're going to dive into a groundbreaking concept, OCR-Memory, vision as the new agent memory. For a long time, autonomous agents have relied on text, but we're proposing a massive modality shift, moving from text to visual tokens to completely shatter the traditional context window limit. To understand why this is necessary, let's look at the bottleneck we face today. On one hand, autonomous agents operate in continuous streams and need to reference incredibly rich, multi-step interaction histories. On the other hand, storing all these raw text trajectories is prohibitively expensive. Our LLMs have finite token limits, and the context window simply cannot hold everything. So, why does text fail? If we look at the current memory landscape, paradigms like standard retrieval-based RAG or context compression struggle. They either lose crucial details, destroy structural fidelity, or carry a high risk of hallucination. OCR-Memory, however, flips the script. It offers the highest token efficiency with a 10x compression, while maintaining perfect, lossless detail and zero hallucination risk. Here is the core insight of this shift. Dense text and complex UI layouts can actually be encoded into visual tokens without losing any fidelity, yielding a massive 10.6x compression ratio at a 32K context limit. The new paradigm is simple: stop storing agent memory as expensive text. Instead, render that history as an image, and let the agent simply look at its past. How does this actually work? The architecture has three main steps. First, we have the visual memory bank, where raw interaction trajectories are saved as screenshots instead of text logs. Second, the optical retriever passes a query to an optical model that scans this visual history. Finally, we use a locate and transcribe step, where the model outputs exact numeric indices to deterministically fetch the verbatim text. The magic behind this optical retrieval is set-of-mark precision targeting. Every text segment in the memory image gets highlighted with a red bounding box and a unique numerical ID. This transforms the messy task of freeform reading into a highly precise point-and-select operation. The model doesn't need to generate text, it just predicts the relevant binary index. And this locate and transcribe mechanism is exactly how we guarantee zero hallucinations. While standard RAG generates text directly, which is risky if the vision model misreads a blurry image, OCR-Memory just predicts the integer index. We then mechanically fetch the exact verbatim text from a secure database, ensuring 100% retrieval faithfulness. To handle really long histories efficiently, we use multi-resolution active recall, moving from vivid to fuzzy. Older memories are saved at a lower 512 by 512 resolution to save visual tokens. But here's the cool part: if the retriever spots a relevant segment in that blurry thumbnail, it triggers dynamic upscaling. It instantly re-renders it at 1024 by 1024 so the agent can read it precisely. We put this to the test in a token stress test, and OCR-Memory thrives under limits. As context windows shrink, traditional text RAG collapses because it loses massive amounts of information. But thanks to dense visual encoding, OCR-Memory maintains high performance. Even at a highly restricted 1024 token limit, we see a massive 14.8% step success rate gap over standard methods. Of course, engineering is all about trade-offs. Let's look at the system efficiency profile. With OCR-Memory, we deliberately trade a bit of cheap local disk space and add a minor 1.4 seconds of latency per step. In return, we protect the most expensive and scarce resource in LLM deployments, the reasoning context window, achieving a massive 6.7x reduction in reasoning tokens per step. In conclusion, the future of agent memory is optical. It offers an infinite horizon with scalable storage, absolute fidelity by decoupling search from generation, and dynamic efficiency through vivid to fuzzy active recall. Thank you.